So I've assumed that you now have worked through the second set of problems, and so we should talk about those next. Um, the first one is, well, water flows gently through an open hose because it receives little energy from the water company. 2, lost energy through its final opening. 3, lost energy as it enters the hose, or 4, lost energy throughout its trip to the hose. What I mean by that is if you come here, and everybody knows this, is that if you have a hose, which say you're just sort of holding and it's going up into the air. I can't draw very well here. The idea is if you just hold it open, then what happens is that you get a little bit of water flow, but it just dribbles out, falls to the ground. It doesn't go very high. On the other hand, if you close off the end with your thumb, then what you know is that all of a sudden you can spray significantly higher up into the air, and you can actually have it leave the hose at a high rate of speed. So why is it that this is a different case than that? And the answer essentially is the energy loss due to flow. Remember, the viscosity dissipates energy, and so the faster that the velocity of water is and through this really long hose, then the more energy actually is lost. So what you're doing by putting your thumb over the end of the hose is that it lowers the velocity in the hose because it doesn't have to deliver so much volume of water, and at the same time the pressure just behind your thumb dramatically increases because without having the energy loss, then the pressure increases. Remember, you can't change the velocity of water through the hose, so it can't go into the hose at a high rate of speed and go out at a slow rate of speed. The only way that it can change the energy is by changing the pressure. So if you have a high rate of speed, then the pressure decreases. And in fact, it has the highest pressure right next to the faucet, and as you go through the hose, the pressure drops, which is why it comes out weakly. And so the idea is here is the 4 is that it lost energy throughout its trip to the hose end. The next one is water's flowing gently out of the garden hose. You block off most of the hose opening with your thumb, and the water sprays out at a high speed because you, 1, are doing work on the water with your thumb and greatly increase its total energy. 2, are keeping air from getting into the hose, reducing the pressure. 3, are compressing the water and increasing its density. And all these don't really make sense. And water's incompressible. You can't change its density. You can't, it's not air that's reducing the pressure, and you're certainly not doing work on it. The only thing that happens is that you slowed the water flow through the hose so that it wastes less energy doing work against viscous forces. And the amount of energy that's lost depends on the flow rate. So the slower the flow rate, then the more pressure head there is at the output, which means that when it comes out, streams out, it goes at a high rate of speed. This is what's happening. So the idea is that viscous effects waste the water's energy, and the viscous effects become stronger with increased flow speed. The faster the flow leads to more viscous energy lost, and faster flow causes a quicker loss of pressure. So again, the only way it can change energy is that the pressure decreases as it goes through the hose. So again, when water pours weakly from an open hose, but sprays hard when you cover most of the end with your thumb, when is more water coming out of the hose? Clearly more water comes out when the hose end is uncovered. When you close your thumb over the top of it, then the water flow decreases, which means that the energy is increased at the output, meaning the pressure goes up. So now the next question is, well, why does water spray so hard from a nozzle? In other words, the flow rate's slow going into the big part of the hose, but when it goes into the next to your thumb, or if it has a nozzle, it comes out at a very high rate of speed. And so really the question is, well, how do you make the water accelerate? Even in a steady state, the water can accelerate. Okay. But the point is, if you had a forward acceleration, it would leave gaps. And if you had a backward acceleration, it would essentially cause jams, meaning that density would increase. So the acceleration has to involve turning. And so the acceleration towards the side involves obstacles, and you have to do it by doing pressure imbalances. And this is what actually changes the speed. So, for example, if you want to bend a hose, the idea is that the water, as it flows through there, is undergoing circular motion. And so if it's undergoing circular motion, then there has to be a centripetal acceleration. And how does it get to that centripetal acceleration? Well, it does it by having a differential in pressure. So at the outer end here, it's got to have high pressure on one side, and it's got to have lower pressure here. And that's what causes to give a net force towards the center of the turn, which is how it turns around. So what it means is that when a hose will fail, it almost always will fail on the outer end of the turn. When you have a 90-degree turn, it won't fail here. Because this is the high pressure side. Water accelerates from high pressure to lower pressure. Now if you go through a nozzle, the water has to speed through the narrow nozzle, and so it needs a pressure imbalance to push it forward. And so you get a pressure gradient. So again, so the Bernoulli equation still works here, is that when the speed is higher here, and we know it's higher here, then the pressure has to go down. Whereas over here, the velocity is slower, and so the pressure has to be higher. There are a couple different things that are happening here. One is that this undergoes circular motion, meaning that this has to be a high pressure point. This is a lower pressure point. Same thing here, is that you'd have to have high pressure here, low pressure there. And when it gets into this section, basically it has to have low pressure here and high pressure here. So the idea is that at this point, you get a high pressure buildup, and the pressure decreases as you go along this side. And so it basically accelerates. You don't get gaps, but the velocity increases. Okay, this is probably a good place to stop, I think. Yeah, I have a little bit of time. Yeah, let's go ahead and stop there. Let's undergo the next set of questions.